What's up, everybody? My name is Rishabh, and today we are going to discuss a very interesting problem which I have faced a lot of time, and I believe some of you would have also faced this problem. So, for the wider audience who might face this in future or are currently facing this problem, this video might help a little. So, let's discuss about the problem. Okay, so let's say you have built a random forest classifier model. Okay, you're working for a client and you've built a random forest classifier model, and the validation or the test accuracy that you have provided them or told them is, let's say, 90%. Okay, the model is good. 90% accuracy, it's not too bad. It's quite good. The client is okay with that. Everything is going fine. Now your next thing that you need to do is to deploy it in production. Okay, next task is to deploy in production. You can deploy it anywhere, whether it be AWS or GCP, any cloud service, it doesn't matter. But the thing is, you told this to client that we are just about to deploy it, and then the client says that there's a critical business requirement that we need to keep in mind while we deploy this model. So what is that? That it's so critical that the client is telling you at this point when you are about to deploy the model. So the critical requirement is that the client is saying there should not be any wrong predictions by the model at the time of prediction, like when it's deployed in production. Okay, so he doesn't want to see any wrong predictions. I mean, it's contradictory because we have already told him that the accuracy is 90%. Now why is he saying that he doesn't want any wrong predictions? So this basically implies that the accuracy that he's looking for in production is 100%, which ideally is not possible. But we might be able to do that. The client might need to do some sacrifice in a few things, but I think we'll be able to achieve it with a simple hack. So if you want to figure it out, just stick to the end. So let's get into this. So let's understand this with the help of an example. So here I'm on Jupyter Notebook, and I'm using the famous MNIST example. So if you're not aware about MNIST example, then you may as well skip the video. Sorry, just kidding. So what we're going to do is we're going to create a random forest model using the MNIST data. So this is the model, and we are going to use the first 1500 rows to train the model and the rest of them to test the model, or basically report the validation accuracy. So I've trained the model up here, it's done, and now let's test the accuracy. So as you can see, the accuracy at the time of validation is around 92%. It's more or less a similar to the case that we were discussing. So this is the validation accuracy, but we want 100% accuracy in at the time of deployment. So we don't want to see any wrong prediction. So we want to ignore the false positive as well as the false negatives. It's, let's say, a binary classification problem. So you can address this problem somewhat at the time of model training, right? You can tune the hyperparameters and things like that, but it's like highly improbable that you'll be able to achieve these kind of results. So this is something that you can try at the time of deployment. So what we're going to do, let me tell you what happens. So let's go to the random forest classifier documentation from sklearn. So the random forest has this predict probability method. Okay, so if we scroll down, so this is the page. If we scroll down to the methods, we can see it has this method called predict proba. Now if you click it, it's going to say that the predicted class probabilities of input samples or something like that. So we are going to use this method, and what this basically does is it'll give the probability for each of those predictions. So let me give you the backend of how this works. So I'll just scroll this down. So as you might be aware, a random forest model basically contains like n number of decision trees. Okay, so let's say the model that we have created has 100 decision trees. Just to give an example, so the trees could be starting 1 2 3 4 5 6 so on and so forth up until 100. Okay, now if we consider our MNIST example, okay, then the labels that we have range from 0 to 9, 0 1 2 uh, 3 and so on and so forth up to 9. So what happens is at the time of prediction, each of those trees for one input, let's say we are considering just one input row. Okay, so for one input, each of these trees is going to give one output. So let's say the first tree says that the output, the prediction according to it should be 0. Second also says it's 0. Third says let's say 6 because they look similar. Fourth says 0, so on and so forth. Let's say the 101 says it's 9. So now we are going to some of those results. So 0 was voted by, let's say, 60 trees. 1 was voted by, let's say, 10 trees, and so on. 6 was voted by 20 trees, and so something like that. So now if you see, the probability of seeing 0 as output is 60 by 100. 100 is the total number of decision trees that we have. So that means the probability of seeing this is 60%. Similarly for 1, it's going to be 10%. So on for 6, it's going to be 20%. And some of these probabilities will be definitely equal to 1. Okay, now what happens? Decision tree would compare these probabilities. So it will compare 60 and 20 and 10 and so on, and it will see like which is the maximum probability I'm getting. So it's 60, and this probability corresponds to 0. That means the output is going to be 0. So that is how you basically see the prediction at the back end of the random forest. Now we are going to use this information, and we are going to put some thresholds on this, and we'll tell the model that when you are actually confident, then you can give us the predictions, else just keep it to yourself, something like that. So let's go back to Jupyter Lab. So what we're going to do, so we have the accuracy and everything. So let's just run the predict probability method. Let's see what do we get. Okay, so if I run predict probability method and give to it the X test column, so it's going to return me these probabilities. Now let's just convert it to a data frame. That will be easier to understand this. Okay, and I'm just going to convert it to list, and as the columns we're going to say the classes, the individual classes that we have, right? So let's just save this in a temp variable. Now if I print this temp variable, then you can see that at the top we have all the MNIST classes starting from 0 up until 9, and here we have all the inputs that we provided. Now you can see the numbers represented on each row, in each cell to be precise, are the probabilities. So for 1, the probability is maximum of 41%, and that's why I think the probability for the first input would be 1. Similarly for second, the maximum is at 90 for the label 7, so the output will be 7 and so on and so forth. So let's do one thing. Let's extract the maximum probability. So what we're going to do is we're going to assign a new column. Let's just call it max prob. Okay, and we are going to say that temp or max with the axis equals 1. And now if I print this, it's going to give the maximum probability. Now what we can do, we can put a threshold on this probability and then calculate the corresponding accuracy. So let's do one thing. Let's just calculate the, just put up the threshold of, let's say, 90%. All right, so now we have 83 rows left. So initially we had 297 rows, but now if we put the threshold, we are only left with 83 rows out of it. So that's basically like 15-20%, I don't know. So that this is the trade-off that you need to bear. You need to address this with client, and you need to tell him that, you know, we can definitely get the accuracy of 100%, but if you are okay with the throughput getting dropped, then we can deploy this solution. Now let's just do one thing. We'll just capture these indexes and we'll calculate the probability. So I'm just going to write index up here, and we're going to store this in an IDX variable. Okay, so we have the indexes. Now I'll just print the accuracies all along, so we can just fine tune the threshold that we have provided up here. So I'm just going to subscript this with IDX, and similarly I'm going to subscript this as well. So now if you calculate, you see I was right. The theory did pan out. So the accuracy here is 100%, but if you look at the throughput, check the length of index, and then we divide it by the length of y test. So it's 28% of throughput. So we are kind of omitting 72% of data. We're not giving predictions for 72% of data, but the accuracy is 100%. So now it's time to play with it. Okay, so let's reduce it to 80%. Accuracy is still 100%, and it got almost doubles. 45% is now the throughput. Let's decrease it further. Let's go to 70%. Accuracy is still 100%, and we have almost 60% of throughput. Only 40% of inputs are missing. Now we'll decrease it slowly. So for 60, okay, 70% throughput, not bad. Now as we get closer to 50% as the probability, then the number is going to drop, the accuracy number. So okay, as you can see, for 55% as the threshold, the accuracy dropped to 99.5%, and the throughput would be close to 75%. So not too bad. The accuracy is almost good. But one thing to keep in mind, don't just try this for one type of data. When you're actually deploying this in production, test this for different samples of data and then finalize on the threshold. Looking at just one data and finalizing, it's a bad idea. And this approach or this technique basically is applicable to all kinds of models that support this kind of probability function or probability attribute. So this can also work for decision tree as well. So that is it for this video, guys. I hope you guys learned something new. If you did, just try and subscribe the channel, maybe like the video, share it with someone else, share it with someone who would find this helpful, and I'll catch you guys in the next one. Bye bye.